Hello, welcome once again to lecture on physics under communication 16.2 modulation. Today we are going over amplitude modulation, frequency modulation, and the advantage and disadvantage of each of them. Let's just review what we have learned before we will watch a short video. Basic about telecommunication system, you must have the information, what I speak, my signal, we call that signal or signal information, or it can be music, it can be speech, message, writing, or your data. You encode it first, encoding device, then you send it, then you decode it before you receive the final information. So basically, we are trying to send information to another person, another place. Right? Transmission, we can use a different channel. Example, you can use optic fiber, you can use the atmosphere or sound waves. And we finish off with going over amplitude modulation for radio transmission. So it can be amplitude, it can be frequency modulation at the encoding process. So the summarize for you, what is modulation? Modulation is the variation in either amplitude or frequency of a wave. Either, right, you have a carrier and you have your signal. Carrier, higher frequency. You must, in some way, change the carrier, either by amplitude or frequency. Right? That is frequency. You change the frequency, but amplitude remains the same for the carrier. Either in synchrony with the displacement, it means that displacement causes the amplitude of the carrier or the dismal carrier to change. Whereas this one, it causes the frequency, right? It's the amplitude or the displacement of that signal causes that frequency to change. Right? Either or in order to carry the information. Right? The information is the one that changes the frequency or the displacement of the carrier. And the carrier is the one that we send. Okay, let's go and look at video before we summarize for you.
What is amplitude modulation, that is AM? When the amplitude of high frequency carrier wave is changed in accordance with the intensity of the signal, this process is called amplitude modulation. In the amplitude modulation, only the amplitude of the carrier wave is changed. The frequency and the phase of the carrier wave remains constant. The first visual shows the principle of amplitude modulation. The diagram also shows the audio-electrical signal of frequency, Fs. The second visual shows a carrier wave of constant amplitude with frequency, Fc. The third visual is the amplitude modulated wave. It is to be noted that the amplitudes of both positive and negative half cycles of carrier waves are changed in accordance with the signal. Thus, the amplitude of the modulated wave possesses the frequency of audio signal waves. Explain frequency modulation, that is FM. When the frequency of carrier wave is changed in accordance with the intensity of the signal, this process is called frequency modulation. In frequency modulation, the amplitude and phase of the carrier wave remains constant. Only the frequency of the carrier wave is changed in accordance with the signal. The frequency variation of the carrier wave depends on the instantaneous amplitude of the signal as shown. When the signal voltage is 0 at A, T, E, and G, the carrier frequency is unchanged. When the signal approaches its positive peaks at B and F, the carrier frequency is increased to maximum as shown by closely spaced cycles. But during the negative peak of signal as at T, the carrier frequency is reduced to minimum as shown by widely spaced cycles. The louder signal causes greater frequency change in modulated carrier as indicated by increased bunching and speeding of the waves as compared with relatively weaker signal. The frequency of an FM transmitter without signal input is called the resting frequency or center frequency F naught, and this is the allotted frequency of the transmitter. When the signal is applied, the carrier frequency deviates up and down from its resting value F naught. The change or shift either above or below the resting frequency is called frequency deviation del F. The total variation in frequency from the lowest to the highest is called carrier swing Cs. Hence, carrier swing is equal to 2 into frequency deviation. So 2 into del F. For the purposes of FM broadcast, it has been internationally agreed to restrict maximum deviation to 75 kHz on each side of the center frequency for sounds of maximum loudness.
Okay, let's go back to summarize what we have just seen. Amplitude modulation. Right? We usually like to use the word synchrony, a state in which things happen more or exist at the same time. Right? Here we are saying that the amplitude of the carrier has been changed at as the same rate as the signal. This is the information of the signal. This is the carrier. This is the resultant waveform. So in amplitude modulation, the amplitude of the carrier wave varies in synchrony with the displacement of the information signal. Right? So that's why we call it amplitude. Amplitude changes in synchrony with the displacement of the information signal. So when it comes to testing, they will ask you, what is amplitude modulation? So you have to memorize it. The bandwidth of broadcast is 9 kilohertz. And amplitude modulation we use for the waveband 30 kilohertz to 30 megahertz. It means from the medium wave, short wave, and long wave. And that's a carrier, often a radio wave, right? Or it can be light wave, it can be alternating current. It's the means we send the information. So it usually has a higher frequency than the information. As we say, higher frequency, greater intensity. Greater intensity means it can go further distance before we have to amplify it, or before we need another amplifier to make it bigger, to send it further. So we give it a frequency FC, frequency of carrier, amplitude A. Okay, you find the period, or the period can calculate the frequency of the carrier. Unmodulated, that means by its natural form, it cannot communicate any information because it's a carrier. Modulation is a fundamental to communication process. That is a speech. Right? Don't be frightened by that. Actually, it's make out a lot of sine curve from small amplitude to large amplitude from different wavelength. That's all. But we're not worried about that. Usually we use a monotone, like this one. Okay? We represent our speech as information signal. Right? Information signal, it can be our audio, can be our video, can be our data. For experiment, we do experiment, the data, which is usually changed all the time, right? It's changing all the time and can be highly complex. So we are just using a pure tone here, and it has a frequency FA, the period is TA, and the amplitude, right? A for audio. Amplitude is AA. Now we can compare analogy of a carrier, human and radio communication. Human carry the baby. Right? Instead of radio communication, it is a signal information. Carrier must be taller. Right? Must be taller. Then the carrier for the radio communication must be larger amplitude. Carrier must be stronger. Greater strength. Have greater strength. You know how to carry the baby. Carrier for the radio information must also have high frequency. High frequency, greater intensity, as the intensity is proportional to frequency squared. Okay, so that's AM. The sound wave, we change it to alternating current, and then the amplitude modulator combine a carrier plus an alternating current to produce the amplitude modulation carrier wave. Basically, it's just a signal. Right? There's a signal or information sitting on the carrier wave, that's all. That's what carrier is all for. Variation of the amplitude of carrier wave is a measure of the displacement of the information signal. So you can see that exactly the same as the signal. Right? So we call this the envelope. Right? The envelope. That's the envelope. And the envelope gives you the signal. And if you want to find the frequency of the signal, we just take the from maximum to maximum, find the period, and then invert it to get your frequency. That's the period of the information. Rate at which the carrier amplitude vary is equal to the frequency of the information signal. How often I go from maximum to another maximum. So that time give us the period of the signal. How fast the carrier changes, how fast the amplitude of carrier changes, where we call the rate. Right? That is the period. So that period gives us a period of the signal. Right? The signal doesn't have to be sinusoidal. It can be any shape, like the red one. Carrier is the green one, and it will sit on it on both sides. Right? What is sideband and bandwidth? Frequency for AM. Right? What are we interested in? Frequency spectrum shows a frequency that are present plotted on the x-axis, right? The different frequency plotted on the axis, and the relative amplitude shown by the height of the vertical line. Right? Remember, it doesn't have to be amplitude. We can plot it with power, or we can plot it with intensity. Intensity is proportional to amplitude squared. Okay, so carrier FC. That's your frequency axis, that's amplitude axis. So amplitude modulator waveform is analyzed, is found to compose of three different components. Our carrier frequency, and on either side, there is the amplitude, carrier frequency amplitude. As I said, this can be power or intensity. So that will be your A. Then you have your sideband. Sideband, on either side. FA, remember, is the frequency of audio. So your FC plus FA, FC minus FA. Amplitude will be just half AA. Okay, so we have a FC and FC minus FA. Amplitude is half AA, and the upper limit will be FC plus FA. Amplitude is the same, half AA. Okay, so if we have a frequency spectrum for a carrier of 50 kilohertz and the signal is 5 kilohertz, then we can just draw 50 kilohertz for the carrier, and then it got two sideband, one sideband there, one sideband there. This one will be 50 minus 5, 45. This one will be 50 plus 5, so you get 55. So the distance from the lowest to the highest or highest to the lowest is called your bandwidth. And then bandwidth is 55 minus 45 is 10. Or is 2 times the audio frequency. Either way, either you take the maximum frequency and the minimum frequency, or you take 2 times the audio frequency that you send, or the signal frequency that you send. Sidebands are the frequencies generated on either side of the continuous wave carrier. So sideband are on either side of the carrier frequency. It is modulated either by AM or FM by information. So we need to define bandwidth. Right? Bandwidth is the largest frequency minus the smallest frequency, right? Or FC plus FA. This is the one largest. This is the one smallest. So FC minus FC is 0. You got FA minus FA is 2FA. Bandwidth is the frequency range occupied by AM wavelength. The bandwidth of AM signal is 2FA. Okay? Don't get confused with electronic. We use the same idea. Right? Bandwidth, basically, this is the frequency that we want to send. So this is the frequency that we want to amplify with the same amount, the same gain. Right? That's the electronic part. Electronic part, bandwidth is all the frequency that are amplified with the same gain. Okay, this is just repeat, that's all. That's your AA. That's your A plus AA. That's your A minus AA minimum. And then remember that the frequency of carrier must be greater than the frequency of the signal. And the amplitude of the carrier must be greater than the amplitude of the carrier must be greater than the amplitude of the signal. And remember the principle of superposition, where we add these two waves to get the black one, or we add the green one and the red one to get the black one. Right? The thing to remember, the one with the largest amplitude, like this red one, greater amplitude than the blue one, so the blue one will be sitting on the red one. Same here. Right? The green one will be sitting on the red one. Black is the resultant. So the frequency, if the lower frequency has greater amplitude, then becomes a carrier. Okay, so in this case, the original frequency disappears. Maximum amplitude is your, we add the wave, remember? So we have A is for the carrier, plus the audio A, so that's the largest. Minimum is the A minus your AA. And as you have stressed, the carrier frequency must be greater than the information frequency. And the amplitude of the carrier must be greater than the amplitude of the information. Right? Remember, normally, this is also amplitude modulation, right? Not by a monotone, not by a sine curve, but it can be a complicated waveform. That means a lot of different sine curve. So many audio frequencies are involved in this case. It can be seen that the bandwidth for AM waveform is the range of frequency from the lowest to the highest, and it's the sideband. So in this case, if we are required to draw, right, it's not monotone, then we have our, this one 50, 50 is our carrier frequency. Right? Example, for music that's broadcast on a range of frequency 30 to 4500 Hz. Okay, we can write it in kilohertz here. Okay, so the center one, if the carrier is 50, can write 50. Right? If it's not given, then we write our F, carrier frequency, then carrier plus 4500, the largest part here, and then carrier minus the largest value, carrier frequency minus the largest frequency, we get this value. Same thing. Now we'll work with this one. Right? The smallest here, F minus 30. Same thing here, F plus 30. Here we are not sure about the amplitude, so it doesn't matter. We just give it a variation. It can go up if we want to. It doesn't matter. Just to illustrate only that there's a range of frequency. The bandwidth is still this part, largest to the smallest. Okay? So that's your bandwidth. That's how we get our 9 kilohertz. Okay, the next one is frequency modulation. Okay? Remember, this is low frequency. This is amplitude. This is time. Right? This is low frequency. This is medium frequency. High frequency. More waveform per unit time. FM uses electrical image of a sound wave to modulate the frequency of a carrier wave. So basically, this frequency modulation, when we say image, we are saying alternating current that correspond to the sound frequency, to the sound variation. So that's the carrier, that's the signal or information, that's the resultant waveform or the modulated waveform. Frequency of carrier varies in synchrony. That's the term you may need to remember. And it means the frequency carry, the amplitude changes fast, the frequency changes fast. If the frequency changes slowly, if the amplitude changes slowly, then the frequency also changes slowly. The frequency of carrier varies in synchrony with the information signal. If we look at this part there, where it's 0, frequency more or less follow the same thing as here. 0 displacement, frequency doesn't change. And if we look at the 0 there, where the amplitude of the signal is minimum, this part there, minimum, frequency also becomes the lowest here. Resultant waveform have constant amplitude. Amplitude doesn't change. Remember that. Frequency modulation, the amplitude of the carrier doesn't change. It remains constant. The carrier frequency still must be greater than the signal frequency. Change in frequency measures the displacement of information signal. Rate at which frequency varies if the frequency of the information signal, that means like this case there, is a minimum here, is a minimum here, that's the rate. So that gives you the frequency. You have to calculate the period between this part, calculate the frequency of the information signal, and then they give you the rate of change of the carrier frequency. So this one is used in the 30 to 300 megahertz waveband, or we call it very high frequency. Just give you a special name as a distinguish from other waveband. Right? So minimum amplitude, minimum frequency here. Right? Where we see maximum, then we have maximum frequency here. That means the waveform are closer together. And then from 0 to, sorry, okay. Okay, from that 0 to that 0 is your period. And that's how we find the frequency of the signal of the period. So from 0 to maximum, or from a 0 to a minimum, that's called your frequency division. How the frequency change from a maximum to a lower, to the value of the carrier. Okay, this one just to explain to you. Where it is 0, the frequency is more the same. And remember the stress, carrier frequency must be very much greater than the signal frequency. And this is a carrier, sorry, this is a carrier wave, this is a signal wave. And that's the resultant, or the frequency modulation waveform. And where there's a maximum amplitude, and there's a maximum frequency here. And minimum frequency around here correspond to minimum here. And then the frequency deviation is just the maximum that it changes minus the carrier frequency. Or it can also be carrier frequency minus the minimum, same thing. Okay, so if we take maximum, it changes to minimum here and change to maximum. And the frequency is the frequency of the signal. Right? That's what we have said. And that's the amplitude of the signal. And usually, right, we give you how the amplitude modify the frequency by that deviation, delta F divided by amplitude, and this is always in kilohertz per volt. Okay, same as AM, except here we have there's your sound signal, change it to alternating current. But here we use frequency modulator. We combine the carrier wave and the alternating current, and that is your frequency modulation. When information is broadcast for FM radio station, the electrical image of the sound taken from the microphone, that means the alternating current that corresponding to the sound wave, is used to modulate the frequency. Right? Alternate current modulate that frequency. Right? Whereas AM, we change this amplitude. Okay, as I say, the signal doesn't have to be sinusoidal. It can be any form, can be any complex form, but you need to identify minimum here, minimum frequency. Maximum here, high frequency here. Zero here, original frequency. Okay, let's look at a simple example. A 40 kilohertz sinusoidal carrier of 8 volt, right? Is 8 volt. Is frequency modulated by 2 kilohertz. That is your signal or information. Amplitude is 3 volt. Behavior of the carrier is governed by the frequency deviation. That's a frequency deviation, 2 kilowatt per volt. Describe how the FM signal changes with time. Then after that, you are told, describe how the FM signal will change if the information signal becomes forward. Instead of 3 volt, it changes to forward. Right? Identify where is your FC. Right? And then the amplitude of your carrier, remember, is constant, it doesn't change. And your frequency of the information or audio. That's your amplitude of the audio or information. And this one should multiply that to get the frequency deviation. Right? Not this one. Not this one doesn't change. It's the audio that change the frequency, of the information. So frequency deviation, we just take your 20 times 3. Right? It's the amplitude of the information. It changes the frequency of the carrier. So it means that it changes, the carrier frequency will change from carrier plus 60 to carrier minus 60, the minimum. So if you look at where it has the same frequency, then that rate of change is 2 kilohertz. Right? 8 volt stays the same. Okay, let's summarize that. Calculated, what we have calculated that carrier frequency is given, information frequency is given, there's a deviation. So the resultant carrier will change in frequency from 400 to 460, 400 plus 60, 460, and then 400 minus 60, 400 to 240, and back to 400, and repeat with that frequency 2000 times, right? Either 2000 times or 2 kilohertz. This is because the frequency deviation we have calculated throughout the carrier amplitude remains the same. If the information signal amplitude is forward, right? In this case, if it's forward times your 20 is 8 volt. 8 forward times 20 is 80. So it will go from 400 to 480 to 400 to 320. Right? 400 minus 80, 320. And if you have changed the frequency, then it will be the new frequency, though, 400 kilohertz. Let me just check frequency as a frequency change. 4 volt only. For the carrier, still the same. Sorry. Okay, so it changed from frequency has not changed. 400, that's the original value, change to 480, then come back to 400, then go to minimum 220, and back to 400 kilohertz, and again is 2000 times per second. In this case, the frequency deviation is no more 60. Frequency deviation is your 4 times 20 is 80 kilohertz. Amplitude still remains the same. Amplitude of carrier still remains the same. Right? Maybe we can summarize here. There's your carrier, 400 kilohertz. There's amplitude 8 volt. There's your signal there. Frequency FA. Frequency deviation delta F divided by A. Right? Amplitude, A is the amplitude of the signal. Amplitude deviation is always in kilohertz per volt. That's the resultant waveform. Combining these two together, amplitude is constant, and that's the amplitude of the signal A. Right? And your tau is 3 volt. So from this formula, take that one across there. That's why we get D times A. That's your D value times your A. A is that one there. So that's why we get 3 times 20. And that's how we get our maximum frequency, this part there. That's maximum. So we got maximum frequency. So it's carrier 400 plus that 60, 460. Same, minimum here, minimum frequency here. So in this case, the carrier frequency, which is this one, minus your 60 is 340 kilohertz. Right? So as I say, we want to get our deviation, the frequency deviation, we just take the largest value, this one, minus that, or this one, minus that also will give you this value, deviation, which is 60. And then that change there, the rate how it changed from maximum to minimum, back to maximum. Right? That rate is the frequency of the signal. This one. That is the one that control how often the frequency changes. Right? To 2 kilohertz or 2000 times per second. Okay, attenuation and noise. Noise is the sum of all unwanted energy. We don't want this energy, that's why we call it unwanted. And it's added to the information signal. Right? Remember, noise is amplitude or energy. So it's added to the information signal. All communication signal pick up interference and noise. And this noise affect the amplitude of the carrier. Right? The noise add to the amplitude. The noise can be motorcycle there. Somebody starting a motorcycle and you turn on your radio and your area will pick up the noise. So you just add it, it's random. So there is the analog signal. Right? You send it out, it becomes, we call attenuated. At the same time, you can see the noise there, right? Very high frequency on top, sitting on top of the waveform there. Signal pick up noise and amplitude becomes smaller. That's what we can observe. So amplitude is the decrease, attenuation is the decrease of amplitude of wave due to loss of energy. You lose energy, amplitude becomes smaller as the wave travel along a transmission path. Example, a wire pair, coaxial cable, or optic fiber. Right? If it's in wire, we can understand as the electron move through, there's resistance. So your energy is lost. Right? Your power dissipator is I square R. The energy becomes smaller as you go further and further away. Right? Or we can either say energy loss or amplitude decrease or progressive power loss. Same, it can be digital signal. Any signal, it doesn't matter whether it's analog signal, digital. If we come, there will be attenuation to pick up the noise there. As it progresses, whether it's analog or digital, as it progresses along the transmission line, can be air, can be cable, it suffers from attenuation and noise. Attenuation increases as length of transmission path increases. As it goes further and further, the amplitude becomes smaller and smaller because it loses energy. Amplitude becomes smaller. We say loses energy. Signal pick up also noise. Two things, remember. And when we repeater, repeater amplifier, it amplifies that attenuated signal. We not amplify the amplitude, we also amplify the noise. The repeater cannot get rid of the noise. Just amplify the noise. Signal pick up noise. Both signal and noise are amplified by the repeater. Can't do anything about the noise. The noise is picked up because it's random in nature. So it will be amplified by the repeater amplifier. Uses of repeater in radio. So the longer the distance a signal must travel, the weaker it gets. It means amplitude becomes smaller and smaller. So if you don't amplify, we cannot hear anymore. So if you want to go further distance, you have to amplify it and send it further. This phenomenon is called signal attenuation. Repeaters are very essential since it boosts the signal, it amplifies the signal, it boosts the power and reduces the signal attenuation drastically during radio communication. Then you can go further. If not, it becomes indistinct as you go further and further. So we need a repeater amplifier to amplify the low signal. Comparison of AM and FM. Noise. AM system, where the information is contained in the amplitude. Remember the AM amplitude of the signal change the amplitude of the carrier. So the noise also affects the amplitude. Noise adds to the information and it pollutes. In FM, it's different. There's no information from the amplitude of the carrier. That noise can be picked up, but it doesn't matter because we are not interested in the amplitude. It can be whipped out at the receiver end. So FM is inherently less noisy than FM. Thus, signal to noise ratio is greater for FM than AM. Okay? For a simple reason, we are interested in frequency. We're not interested in the amplitude. So noise affects the amplitude. So we can whip it out in FM system. So FM, in terms of quality, it has no noise. Bandwidth. Right? For long wave and medium wave, that's your AM. The bandwidth is about 9 kilohertz. Remember, 2 times FA. FA is the frequency of the information. So it means that the maximum audio frequency that can be broadcast is 4.5. So 4.5 times 2, you get 9. This frequency is well below the highest frequency audible to the human ear. Human ear can hear frequency up to 15 kilohertz. So if we allow only 4.5, they can see that. Right? That's why AM, the broadcast lack higher frequency. Yeah, can still understand the speech that has been spoken, right? But sometimes it's not that clear. Right? We call that quality. Quality of music or very high frequency range, what I say, or FM. Right? FM is here, more than 30 megahertz. So the bandwidth is 200 kilohertz. So it's more than audio frequency. Right? Audio frequency is 15 kilohertz. So the quality of music received on AM is poorer than FM on the basis of bandwidth. Okay, that's your frequency band, waveband. Right? Yeah, gone over that earlier, just to review. So number of stations for long wave occupies a region of spectrum. We look at an example, long wave waveband, where you use amplitude modulation. Right? The waveband used, let's say, is 30 kilohertz to 300 kilohertz. Number of separate AM stations that could share this waveband. Right? They can use this frequency from this region. How many radio stations? You take the highest one, 300 minus 30. Right? That's all the frequency that's available. Each station is given 9 kilohertz. You divide by 9, so you get 30. Whereas, remember that your FM, the bandwidth is 200. So it's 270 divided by 200. It can only have one only. So that's not good. I can only have one station. So more AM station than FM station can share any waveband. Okay? For region, one waveband. AM, there can be more stations. FM, one only. If you use your long wave waveband. So that's why we never use for long wave waveband for FM. We use in excess of 1 megahertz. Range and cost. AM transmission can go large distance. We'll study this later on. And can be from the atmosphere, and the ionosphere can be reflected back and reflected back from the Earth's surface. So AM chip, because it can go longer distance, we save on amplifier. We save on the receiver and then we transmit again. AM transmission on LW, MW, SW waveband are propagated by very large distance, so the broadcast can be made very large area from one transmitter. One transmitter, you can send your signal to very far away. FM transmission have a range of 30 kilometer by line of sight. That means sight means straight line. Transmitter and receiver can see each other, then they can receive it. If the transmitter and receiver cannot see each other, they cannot receive the signal. To broadcast over a large area, need many FM transmitter. Okay? You want to broadcast over a large area using FM, we need many transmitter. So it's going to be costly. So it's much cheaper in the AM broadcast than FM. Okay. Electronic wise, AM transmitter and receiver are electronically simpler and cheaper. And they also occupy smaller bandwidth. We have gone over that in FM. Whereas FM, the electronic are more complex and more expensive. Right? We can summarize that comparison of AM and FM. Noise for AM, noise pollute the information signal. Right? Whereas FM, noise pickup can be waved out at the receiver end because we are not interested in amplifying the amplitude, we are interested in the frequency. Bandwidth for AM is 9 kilohertz, and we have calculated we can only have 30 station. Whereas if we use the same bandwidth, low, long wave, then for FM can only have one station. Quality for AM is poor because higher frequency cannot be transmitted. Whereas FM, all the frequency are transmitted, so it's very good. Cost, transmitter and receivers are electronically simpler and cheaper for AM. It's more expensive for FM. Range, AM can propagate over long distance. Range for FM is only 30 km line of sight. Advantage of FM, we can summarize: less noise, less interference, greater bandwidth, better quality. Disadvantages: short range, short distance only, can travel short distance only. More transmitter, they become more costly. More complex circuitry, so that explains the electronic also more expensive, greater expense. Okay, so line outside, slide outside, straight line. Okay, let's go to try some example. So I've gone over the theory. So some example. This is 206. Radio communication may be either frequency modulated or amplitude modulated. Explain what is meant by modulation. Right? This is knowledge or memory work. 2 mark there. So memorize it, you get your 2 mark there. Variation in either amplitude or frequency of wave, either in synchrony with displacement information signal. Right? With the one that you can use in order to carry information on the wave. Either one. Amplitude modulated radio wave is to be used for broadcast of music having frequency 30 to 4500 Hz. Radio station is the broadcasting of a long wave band 1 kHz to 10 kHz. Right? That's a long wave band. The bandwidth of broadcast memory work. Right? Two times the highest one, 9 kHz. Okay, highest one, multiplied by 2, 9 kHz. Maximum number of stations that could operate simultaneously in the same area with long wavelength. Right? We have to work with frequency. Right? For 100 meter, using the speed of light, frequency is speed of light divided by wavelength. Right? That's 10 to the power 3, 1000 10 to the power 3. You get 3 times 10 to the power 5 Hz. Then at 10 to the power 4 meter, right? For 10,000 meter, same speed of light divided by that wavelength 10 to the power 4, get 3 times 10 to the power 4. So that's your frequency range. So LW is from 30 kilohertz, right? If I work from here, 30 kilohertz to 300 kilohertz. The number of stations, remember each station is given 9 kilohertz bandwidth. So it's 300 minus 30 divided by 9. So it's 270 divided by 9 is 30. 30 stations. Each station is given 9. 9 bandwidth, 9 kilohertz bandwidth. On figure 15.1, sketch the graph. Okay, basically 15.1 they have given you an empty place there. Okay. On, on the axis of figure 15.1, sketch a graph of a typical power spectrum for radio station. It doesn't have to be amplitude, can be power, can be intensity. Label the axis with values of the frequency. Right? That frequency can be in be in kilohertz. Okay. Right? We are given the range of broadcast for the information 30 to 4500 hertz. Carrier frequency are not given, so we call that F. So we put that as F. And then the highest one is F plus 4500. It should be hertz.